Calculus is all about rates, and one main example of rates is velocity. Remember, velocity is the derivative with respect to time of your position. Right? Velocity measures how quickly your position is changing. Here's a particularly nice example that we can look at. A car driving past you. So I've drawn a diagram of the situation. I've placed you at the origin. So your coordinates are 0, 0. And I've placed the car here at this red dot. Its x-coordinate is vt. I'm thinking of v as the velocity of the car and t as the current time. And I've placed its y-coordinate at b. So the car is going to drive along the line y equals b at a constant velocity v. Let's compute how far the car is from you. So I've drawn a line segment between you and the car. I don't know how long that line segment is. Well, imagine an invisible right triangle here. I can use a Pythagorean theorem to measure the length of this hypotenuse if I know the lengths of the two legs. This horizontal leg has length vt, the vertical leg has length b, so the length of this hypotenuse, the length of this line segment, is the square root of the sum of the squares of the lengths of the legs of the right triangle. How fast is the distance between you and the car changing? So I want to know how fast the distance between you and the car, is changing. So I take a derivative with respect to t. So this is the derivative of the square root of something, and the derivative of the square root function is 1 over 2 square root. So I'm going to be evaluating the derivative of the square root at the inside, which is vt squared plus b squared, times the derivative of the inside function. So the derivative of vt squared plus b squared. Now I'll just copy down the same thing, 1 over 2 square root vt squared plus b squared times, what's the derivative of this? Well, it's the derivative of vt squared, so that's 2v squared t, plus the derivative of b, which is 0. So now I could write this all together. I could, for instance, cancel this 2 and this 2, and get that the derivative of the distance between you and the car is v squared t over the square root of vt squared plus b squared. Let's take a look at this with a graph. So here's a graph of that function. Remember, that function is the derivative of the distance between you and the car. So it's negative over here because the car's distance to you is going down, and it's positive over here because the car's distance to you is increasing. You can look at it here as a little tiny model. Here's the car, here's you, right? The car maybe starts over here and then it drives past. And how does the distance between you and the car change? Well, here the distance is getting less, 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 less. So it's as close as the car gets to you, more and more, further, further, further away. And that's exactly what you see from this graph, right? The derivative's negative here because the car is getting closer to you. It's 0 here when the car is as close as it ever gets to you. And the derivative is positive over here because the car is getting further away from you. We can hear this in one of the explorations on the website. Here I've got a car that's driving past, and here in blue is you, the observer. Listen to what happens when I turn on the sound. Higher frequency and lower frequency, higher, lower. You're hearing the derivative.